Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on September 1st, 2025, which was about 7 days ago. The standout result is a general robot manipulation policy that generates precise actions in just 1 to 2 inference steps, while more than doubling real robot success rates compared to a strong 3D diffusion policy. The paper is titled ManiFlow, a general robot manipulation policy via consistency flow training. And as we will see later, the gains come from both training and architecture choices. In brief, the method couples flow matching with continuous time consistency training and a multimodal transformer, delivering strong robustness, scaling, and bimanual and humanoid dexterity. On X, a robotics account highlights ManiFlow's 1 to 2 step action generation via flow matching, continuous time consistency training, and DiT-X fusion, noting dexterous, general manipulation. Engagement looks moderate with about 170 likes. The previous segment set up why fast, few-step action generation matters. Figure 1 showcases what that looks like in practice, with panels illustrating pouring, grasp and place, and a hand-to-hand handoff. The top row depicts dexterous pouring, where the hand rotates the cup smoothly, which signals precise control. The middle panels show grasping varied objects and depositing them into bins, so the policy handles shape and texture changes. The bottom sequence highlights bimanual transfer, indicating coordinated timing across 2 arms. So the previous figure highlighted the behaviors. Figure 2 shows how the policy turns multimodal inputs into actions. The pipeline takes 2-dimensional images or 3-dimensional point clouds, robot state, and optional language, encodes them into tokens, and feeds them into a DiT-X transformer. The transformer fuses these tokens with noisy action tokens and outputs an action sequence. Flow matching and continuous time consistency training jointly shape the transformer so the ordinary differential equation solver reaches accurate actions in 1 to 2 steps. Alright, the previous figure outlined the multimodal pipeline. Figure 3 explains the consistency training that makes 1 to 2 step action generation possible. The diagram shows a flow trajectory from noisy actions at time 0 to target actions at time 1, with intermediate points labeled xt, xt1, and xt2. The model predicts velocities between these points conditioned on delta t, and training enforces that every intermediate point maps back toward the same origin, so the path stays straight and consistent across steps. Well, Figure 4 contrasts 3 transformer blocks and highlights why the fusion works. The left panel shows DiT with only self-attention, which limits interaction between inputs and action tokens. The middle panel adds basic cross-attention, yet it lacks adaptive conditioning, so modulation stays coarse. The right panel presents DiT-X, which inserts adaptive cross-attention and applies AdaLN-Zero conditioning to both the inputs and the outputs, with learned scale and shift that depend on time step and delta t. This setup enables precise mixing of low-dimensional robot state with high-dimensional perceptual tokens. So the previous figure contrasted the transformer blocks. Table 1 reports what that buys in simulation. Table 1 shows success rates across RoboTwin, Adroit, and DexArt, plus an overall average. The 2-dimensional ManiFlow policy leads the image group with a 56.5% average, which clearly beats diffusion and standard flow matching. In the 3-dimensional group, ManiFlow reaches 66.5% on average, because the adaptive fusion and consistency training translate into higher scores across all 3 benchmarks. 2 takeaways stand out. First, fast 1 to 2 step action generation works in practice because consistency-trained flow matching keeps trajectories straight, so inference stays accurate and cheap. Second, adaptive DiT-X fusion unlocks general, robust dexterity across inputs and robots. The broader implication is scalable, versatile manipulation policies. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.